The first week of this course is devoted to an overview of manufacturing systems engineering. We'll start off with a case that illustrates some of the issues. Inkjet printers were introduced in 1993. They were much better than the dot matrix printers that were all that was available before. They had much better print quality, they could print graphics as well as text, and they were much faster. The demand for inkjet printers was large and it grew rapidly. Market share is very important to companies when new technology is introduced. Customers are thought to have brand loyalty. Once they get accustomed to one brand of a product, they stay with that brand when they replace that product with a new model. In addition, printer customers don't just buy printers, they also buy ink cartridges. This is also a lucrative market. Consequently, companies are often willing to forego initial profits for greater profits later. Manufacturers could sell all they could produce. Demand was much greater than production capacity. Hewlett-Packard was designing and producing its printers in Vancouver, Washington, near Portland, Oregon. Their initial production was done manually. They decided to increase their printer production rate. In deciding how to increase their production rate, they had to satisfy certain constraints. The first constraint was that they had to keep quality at a high level. Quality does not just refer to the way printed pages look. It also refers to the reliability of the product. The printers have to last long enough to satisfy customers. It was not enough to increase production rate to keep up with demand. To increase market share, they had to increase production at a greater rate than demand. Their production target was 300,000 printers per month. Their capacity with existing manual assembly was only 200,000 printers per month. In addition, they also had to meet profit and revenue targets. To increase market share, however, they had to keep costs low to attract customers. Keeping costs low was also necessary for profitability. They wanted to have a stable workforce. They did not want to have to hire people when demand was high and then lay them off when demand dropped. HP invested $25 million in Eclipse, a new system for automated assembly of the print engine. This is a diagram of the whole production process. Raw materials are fed into the mechanical assembly cell, which we're going to focus on, the Eclipse. The completed print engine went into a storage buffer, and from there it went to final assembly with the rest of the printer, and then to packaging and shipping. Altogether, 2 of these Eclipse systems were installed. This is a representation of the Eclipse automated assembly system. There are about 100 steps in the manufacturing process. There was a main loop and several subassembly lines feeding it. The base was assembled in the first subassembly line, and additional subassemblies were added to it later. The main loop had 30 workstations. When the base entered the main loop, it was attached to a pallet which would carry it through the assembly process. This reduced possible damage to the product from being clamped at each station. Each such clamping risks damage. Clamping the pallet causes no damage to the product. When the assembly process was complete, the engine was detached from the pallet and then sent to a storage area to await final assembly of the printer. The empty pallet was sent back to the first assembly station to get a new base to carry into the main loop. At the time when this was all happening, the American industry consensus was that inventory was bad and should be eliminated. As a consequence, the system was designed with very little room for inventory. As we will see, inventory is a necessary evil if there's variability in the manufacturing process, and there's always variability in the manufacturing process. Some assumptions were made about the system. Efficiency is the fraction of time that machines are available for production, not needing or undergoing repair or maintenance or any other activity like that. We'll describe that in more detail later. The operation times at each station were estimated to be 9 seconds and constant. Consequently, the total production rate was estimated to be about 370,000 units per month. But after the first 2 stations were installed, data was collected, and it was found that efficiency was less than 99%. Operation times were variable, often greater than 9 seconds. In that case, actual production would be about 125,000 units per month. A very disappointing result. They then faced the problem: how to modify the system to increase production rate, and how to make the changes happen in a very short time. The reason for the drastically reduced production is the effect that the failure of one machine has on all the others. In this animation, the 3rd subassembly line fails. While it is out of action, the upstream part of the main line keeps operating for a short time, but the parts accumulate on the transportation system. They create a traffic jam, and all of the upstream machines have to stop because they have nowhere to put their completed parts. They're blocked. At the same time, the parts that were downstream of the failed machine are processed until they leave the system. At that point, The machines downstream of the failed machine have nothing to work on, and so they have to stop. They're starved. When the failed machines are repaired, production resumes. But perfectly operational machines were forced to be idle because of the failure of one machine. This is a loss of productive capacity. Simulation is a modeling technique for predicting performance of a complex system. HP tried to analyze the system by simulation. They consulted a vendor, but the project appeared to be too large and complex to produce useful results in time to affect the system design. This was because they tried to include too much detail in the model. Some conceivable changes were out of bounds. They could not add labor and they could not redesign the machines. A visiting researcher proposed a feasible change, adding a small amount of buffer space within the eclipse. Here's a graph that shows the relationship between buffer space, N, and production space, P. The horizontal axis is buffer space, the vertical axis is the production rate. The graph shows that when there's very little buffer space, adding a little can increase production rate by a lot. This is not true when there's a lot of buffer space already. The underlying design and analysis tools will be described in the second part of this course. Here's a diagram of the modified system. There's an empty pallet buffer. There's work in process space between subassembly lines and the main line. There's work in process space on the main line. And the buffer sizes were large enough to hold about 30 minutes worth of material. This is a small multiple of the mean time to repair of the machines. 30 minutes represents about 200 parts. Here's the old system and the new system side by side. You can see the difference. When this was implemented, it led to increased factory capacity, up to over 200,000 units per month. The increased space on the system is what allowed the increase in production rate. Now, if a machine fails, more time must elapse before the upstream traffic jam occurs. This allows the upstream machines to work longer before they are blocked. Similarly, if there are more parts downstream of the failure, the downstream machines can process more parts before they're starved. Consequently, less productive time is lost due to the single failure. The capital cost of the changes was about $1,400,000. The payoff was great. The incremental revenues were about $280 million. The labor productivity increased by about 50%. This was successful because there was early intervention. That is, the analysis was done before too much of the system was built and already in place. The rapid response was possible because much of the relevant research work had already been done. The HP managers were quite flexible, possibly because of the crisis that they were facing. The new analysis tool was fast, easy to use, and was at the right level of detail.